Hello, my people. Um, Today we are going to talk about thermodynamics a little bit and the difference between an endothermic and an exothermic reaction. So we're starting a new chapter, and this chapter is a lot more fun when you can do stuff in the lab because there's a lot of cool stuff you can do. But we'll have some pivot interactives and stuff that you guys can get down with. Number one, or the first thing I want to talk about is thermodynamics. This thermodynamics is thermo refers to heat, and dynamics refers to relationships. So thermodynamics is the study of heat slash temperature and their relationship to energy. Okay. Heat, you need to know this is super, super important that you know that heat is a form of energy. Whether you want to call it heat or thermal energy or another term you're going to see is enthalpy. And that is the quantity of heat. And you're going to see this enthalpy as H. And what you're going to see in a lot of these reactions is talking about delta H, the change in enthalpy. So, and energy, the energy we're going to use is measured in joules. J. Energy is measured in joules, which you learned last year in physics, if you took physics. Now, here is the most important thing that, like, everything goes back to this, okay? Now, there is potential energy. Stored in the bonds. Okay? There is potential energy stored in chemical bonds. So, in order to break a bond, energy is required. So that is going to take energy. It's going to take energy in order to break a bond. When there is going to be some sort of input of energy. Okay? So an energy input is going to be required to break a bond. And then when bonds are formed, energy is released. Okay? So energy goes from where it was to its surroundings. So now, just a couple of little terms that I want to add in here. The system is whatever you are studying. And then the surroundings are everything around the system. So the environment. Okay. Now, in an endothermic reaction, heat is taken in. Okay. In an endothermic reaction, energy is required for the reaction to take place. Okay, so energy gets put in to the reaction. Now, if you looked at a graph of the potential energy over some period of time, okay, so often when you'll see these graphs, it'll say potential energy here. And what that means is that's the potential energy stored in the bonds of whatever we're studying. And then this will say reaction progress. So it's like as the reaction progresses. Okay. So in an endothermic reaction, you have the potential energy of the reactants right here. And then any reaction has this little hump that it needs to get over. Okay. Oops. I held on too long. Classic. It has this little hump that it needs to get over. And that hump, it needs a little bit of energy to get the reaction started at first. And that is called, even within any type of reaction has this is called the activation energy. Okay. And usually we write that as EA, activation energy. But then for a endothermic reaction, you have the products, and what these lines are, this is the total potential energy stored in the bonds of the reactants and the total potential energy stored in the bonds of the products. Okay. So energy, you can see energy was required to go from the reactants to the products. Okay. So in this case, this is an exothermic reaction because energy was put into the reaction. So energy input, okay, to the reaction. In other words, the potential energy of the products is greater than the potential energy of the reactants. Here's some examples of this. Examples of endothermic reactions might be ice melting. Now, in order for ice to melt, you have all these particles. When you have a solid, you have all these particles in a fixed position, and they have super strong intermolecular forces holding them together, right? When we go from solid to liquid, when it's a liquid, those intermolecular forces weaken, and the liquid sort of moves about each other. Okay. And so these intermolecular forces energy needs to be put in to weaken the intermolecular forces to go from solid to liquid. Okay. So that's an endothermic reaction there. Now, if we talk about an exothermic reaction, an exothermic reaction is one where energy is released. Okay. Now, if we did a quick energy diagram here, that's what this is called, an energy diagram, where we had the potential energy and we had the reaction progress here. What you're going to see is, so you have your reactants here. That's the potential energy stored in the bonds of your reactants. What you're going to see is that you still have an activation energy, okay? You still have an activation energy that this reaction needs to overcome, but then at the end, you are going to see that the products, the potential energy of the products is actually less than the potential energy of the reactants. Okay, so energy is released. Okay, and this right here, from right here to right here, where we the difference in energy between the products and the reactants, that's called delta H. Okay, the change in enthalpy, that's the difference. And in an exothermic reaction, the difference in energy is negative. Delta H is negative because the system loses / releases energy. Okay, so delta H is negative here. Okay, if we go back to our endothermic reaction, we had, so this is the activation energy here, but right here, the difference between the products and the reactants, delta H right here. In this case, delta H is positive because the system gained energy. Okay, so the potential energy of the bonds in the products is more. So the system itself, that's the chemical reaction that we're studying. The system increased in energy, okay, because it took energy in from the surroundings. Okay, so for an endothermic reaction, energy goes from the surroundings to the system. Okay, and then for an exothermic reaction, energy goes from the system to the surroundings. Okay. So in this case, like we said, the potential energy of the products is less than the potential energy of the reactants. So energy gets released into the system. An example of this would be combustion, right? When you sit next to a fire, if you sit next to a fire, then the energy, you can feel the energy going from the bonds that are contained in the wood to you. You can feel that heat energy. Another example would be um, freezing. Because in freezing, like we said, we go from, in this case, we have bonds being formed, right? When something freezes, we go from water where there there's still some intermolecular forces holding them together, holding the water together, right? We remember that water is attracted to itself. The hydrogen is attracted to the oxygen, right? So there's still that, it's called hydrogen bonding. There's still that hydrogen bonding holding the water together, but it's a little bit weaker. But when we freeze, you end up with these water molecules in a fixed place, really tightly bonded together. Okay. And whenever bonds are formed, energy is released. Right. So that's an exothermic process. Okay. Um, uh, Q versus delta H. Q, you're going to see Q is a measure of the heat lost or gained in a certain situation. Okay. Um, so we measure Q in joules, and oftentimes, if Q is really large, we measure it in kilojoules. Okay. And then delta H is the enthalpy change so what that is, it's the heat lost or gained when 1 mole of a substance reacts. Okay, so in this case, oftentimes you'll see delta H in kJ per mole, kilojoules per mole. And then often, if you want to relate the two, Q is equal to, I should probably write it like this, delta H is equal to Q divided by moles reacted. So it's Q divided by however many moles reacted with Q, and that'll give you how much heat was lost or gained per 1 mole of whatever you're studying. You'll find your next assignment is a POGL, and you're going to do a lot with Q and delta H. Please let me know if you have any issues, and have a wonderful rest of your day. Just don't forget to submit these completed notes online. Thank you so much.